Good afternoon, everyone, and welcome to Chase Plastics Chase the Knowledge webinar on understanding polymer modification. This is part two of a five-part series we're calling Chase Plastics 101. My name is Sherry Cudd, and I'm the Advertising and Marketing Manager for Chase Plastics. Thank you all for your interest in this webinar and for taking the time out of your busy day to attend. We just have a few quick housekeeping items before we begin. Everyone except the presenter is on mute and will be for the duration of the webinar. But if you'd like to ask a question, you can do so at any time by typing it in the questions section of your toolbar. If you'd rather ask your question verbally, please raise your hand using the react icon in the toolbar, and I will unmute you and call on you to ask your question out loud. If your question does not get answered right away, we will address it at the end of the webinar. You can access and download PDF copies of this presentation, our product line card, our polymer modification one-pager, and information on our technical engineering team in the materials section during the presentation. You can only access these during the presentation. If you are attending live, a certificate of completion and recording of the webinar will be emailed to you about an hour after the webinar concludes. You will receive a separate email from Andrea with a PDF of the presentation and the handouts. We would greatly appreciate it if you could complete the survey at the end so we can improve future webinars for you and cover the topics that interest you most. We encourage you to check out past webinars and recordings on the webinars page of our website at chaseplastics.com/webinars. If you would like a custom Chase the Knowledge presentation given to your organization discussing a specific topic or material, please send an email to your presenter, Andrea Kendrick, or myself. Our entire sales and technical team are always ready to assist with technical issues, material selection, and educating you and your team on products and processes specific to your needs. Future Chase the Knowledge webinar announcements will also appear on this page as they are posted, including links for this five-part series called Chase Plastics 101, where we will discuss polymer basics, modification. The next one will be on testing, and then fabrication and common polymers. You can register for part 3 on polymer testing on July 30th now. You can subscribe or invite your coworkers to subscribe to receive notifications of all future Chase the Knowledge webinars by clicking that button that says subscribe here for webinar notifications in the right-hand corner of your screen. It's on our website. Another great technical resource is the Chase the Knowledge blogs on our website. They can be found at chaseplastics.com/blogs or under the resources tab from the homepage. We recently added a blog on the advantages of peak in extreme and demanding applications. In addition to our presenter, Andrea Kendrick, whom I will introduce in just a moment, we also have Jim Werwell, Technical Development Engineer, on hand to answer your questions today. So at this point, I'd like to hand it over to our presenter, Andrea Kendrick. Andrea is a technical training engineer with Chase Plastics and has been with us since 2015. She received her bachelor's degree in plastics engineering technology from Ferris State University. For those of you who have attended Chase the Knowledge webinars in the past or contacted our technical engineering team for assistance, you're very familiar with Andrea and the level of expertise she brings to the table. So without further ado, Andrea.
Hey, good afternoon. Andrea Kendrick here. Today, we're going to go over part 2 of our 5-part series, Chase Plastics 101. Today, we are going over polymer modification. Agenda for today, we're going to go over polymer modification. So what is it specifically? We're going to talk about blends and copolymers briefly. We're going to talk about reinforcements and their effect on materials. And then we'll go over additives as well. At this time, if you have the ability to do so, I would download the Polymer Modification one pager from the handout section and have it open, because part of the additives, there's so many of them. I'm not going to go through all of them. I'm going to go through a handful of them, but the one pager has a lot of other ones listed as well with some of their attributes. So a good source to have open as we get ready to go through them. So polymer modification, it expands the use of plastics in application by offering increased variety of property combinations. Essentially, you get into an application, you select a material, and then you find it's not quite getting you where you need to be, maybe from a strength perspective, maybe from an impact perspective, maybe from a heat resistant perspective, whatever it may be, it lines up in terms of quality and need for every other thing, but maybe there's one property that you're just not quite there yet. And so you want to be able to achieve that. And so we can potentially do that by looking at using polymer modification. That's done in three kind of buckets. So a starting one would be reinforcements. So if we add glass fibers, long glass fibers, if we add fillers, which would be your minerals, we could potentially achieve that, again, depending on the goal. We'd also look at using additives, so impact modifiers, different stabilizers, flame retardants, or utilizing a blend or a copolymer instead of the material that we had been looking at. So we'll go through each of these a little bit and talk about them and what they are and what they kind of do to the materials. Okay, polymer modification, blends. So blends are a combination of polymers that take advantages of both. They are the physical blending of two polymers. It is not a chemical change. So in the example given, and one of the more common ones that we have available to us would be PC-PBT. So PC as a polymer, it's amorphous. It has excellent impact. It has low shrinkage, which therefore also results in a low likelihood of warping, but it has really poor chemical resistance. So if you're getting into an application where it's going to see certain type of chemical exposure, it's probably not going to do so well. So in the case of that, you might look at potentially using a blend, PC-PBT, where you could take from the PBT that has excellent chemical resistance and then result in something with good chemical resistance if we're combining it. And then on the flip side, PBT having excellent chemical resistance has higher shrinkage. It's a semicrystalline material. It shrinks more. It also has a higher likelihood of warp. So instead of going from PC to PC-PBT for the chemical resistance, maybe we start with PBT, but we're getting warpage issues, and we add in the PC for the lower shrinkage for better resistance to warp. So overall, if we combine the two, we end up with a material that has good impact, not as good as PC, but it's going to be better than PBT. It's got good chemical resistance, again, better than PC, not as good as PBT, and it's going to have lower shrinkage and lower likelihood of warping than your PBT would, but not as good as PC. So again, when we blend these materials together, we end up getting a nice combination of performances. Other common blends would be PCABS, PCASA. Those are some other common ones you'll see a lot. And so taking the goods from both, or the great performances of both, and blending it to get somewhere in the middle in terms of our performance. And then also remember that this is a physical blend. We are not doing anything chemically to it. It is a physical blend of the materials. Okay, then we go on to copolymers. So this is a little bit different in that this is a chemical process. So during the polymerization process, we will take monomers and we will chemically link them. So instead of blending being physical, your copolymers are a chemical linking. In the case of polypropylene, if we were to look at polypropylene homopolymer versus polypropylene copolymer, the comonomer is ethylene. And so there's a handful of different ways for the material to be copolymerized. If we're looking at the screen, you can see our homopolymer is going to be all one monomer. No changing. In this case, if we are looking at propylene, it's all propylene. So there's no different monomers there. When we go to use a copolymer, there's a few different ways of doing it. An alternating copolymer is every other one changes. So you have your A's being the propylene and the B's being the ethylene. And so it alternates. Then you have what they call a random copolymer. It's going to be random location on it, maybe a couple groupings of B's and A's together, but it's completely random. It's not an alternating pattern. And then they also have block copolymers, where you have sections of the same monomer together. So in this case, a bunch of the A's together for your propylene, bunch your B's together for your ethylene. They also have other copolymers like graph copolymers and other ones as well. Generally speaking, if you're looking at a data sheet or you're looking at the materials, they'll just tell you that it's a copolymer. They might not explain how it is copolymerized and in what structure it comes in, but they'll let you know that it's a copolymer. So polypropylene is going to be one of the more common ones. There's other copolymers. If you look at acetal, you have acetal homopolymer, acetal copolymer. They even make polycarbonate copolymers, some specialized copolymers that exist. And so there's plenty of areas where this can be done to achieve new and different properties. Propylene, for instance, if we're looking at it, tends to be a little bit higher in crystallinity, a little bit better stiffness and strength performance out of a homopolymer. Adding the ethylene allows for better low temperature impact and the ability to improve its impact. So your copolymer propylenes are going to have your higher impact performance, a little more flexible, but your better impact performance. So depending on what you're trying to achieve, if the homopolymer was a little too stiff, maybe didn't have the impact you needed, now we might look at a copolymer. And each of your different copolymers will have different performance functions depending on what's being added, but that would be the example of propylene. Okay, so blends, copolymers, just a quick review. Don't have to go too far into it. So now we'll talk about reinforcements. So another way to modify your material is to add reinforcements. The common ones are going to be fibers, so those are going to be your glass fibers, or fillers, which are going to be your minerals. You can kind of see pictures of them off to the side. This table is to kind of give you an idea of the property changes that these will make. So with fibers, glass fibers, you're going to see a good increase in your stress or your strength of the material. So if it's not quite strong enough, you need a better strength out of the material, you can achieve that by adding glass fiber. What you will see decrease in, however, though, is going to be your strain. So that'd be elongation would be the other term there. So you're going to lose your elongation performance, and you're going to typically lose your impact performance. I say typically because it kind of depends. If it's a really brittle material to start with and you add glass fibers to it, you actually will see an increase in impact performance because then the glass is kind of taken over. But if you take a really impact resistant material like a polycarbonate and you add the glass to it, you're going to see a decrease in its impact performance. It's kind of where there's an asterisk there. And then your HDT, so your thermal performance, you're going to see a boost when you add glass. So the thing there would be your stiffness and strength gets higher. You lose your impact and tensile elongation, and you see an increase in your thermal performance. You will typically see a reduction in your thermal expansion. The glass doesn't really want to move. And then with your shrinkage, you're going to see more anisotropic shrink. So isotropic shrink being uniform shrinkage. So in the flow and cross flow direction, they're going to be uniform. And in front of it, meaning not or without, not uniform. So you're going to see more shrinking in the cross flow direction than the flow direction. And I have a few graphs to kind of point that out and show that in further slides. And then on the other side of that are going to be your fillers, your minerals. So you can see similar effect in terms of property performance. You're going to see a little boost in your stress or strength, a little bit of a loss in strain and impact, and a little bit of HDT performance. So what you're going to find is that it does or improves the same thing that glass does, just not at the same level. And we'll show, again, I have some data for that on some coming slides, but you'll see a little bit of an improvement. The nice thing about it is you're going to have little to no effect on your thermal expansion. So whether you wanted it or not, no effect. Maybe you wanted the reduction that the fibers give. That's to be determined based on what your needs are for your application. But the big one here is going to be your isotropic shrinkage. So instead of imparting a non-uniform shrink on the part like the fibers will, your fillers, your minerals tend to allow you to maintain isotropic shrinkage. And again, I have some data to show what that looks like as well on coming slides. So all this to say, our fibers and fillers are kind of doing the same thing in terms of property performance, increasing our stiffness and strength, generally kind of lowering a little bit our elongation and impact, and increasing our thermal performance. Okay, so now we'll get into each one just a little bit. So glass fibers themselves. So short glass fibers. So as I continue to move on through some of these slides, you'll see SGF, short glass fiber, being referenced. And then we will talk about long glass fiber as well, LGF. These are used heavily in many markets to help increase your mechanical and thermal performance. And then we'll also talk about the downsides of that as well, the data. The one thing I do want to point out is short glass fiber is the standard length for glass fiber. So if you're looking at a data sheet and it just says that it's glass fiber reinforced, they're referring to short glass fibers. They're not going to say short glass fibers necessarily. So the standard length of your glass fiber is going to be what we consider short glass fiber throughout the rest of this presentation. And then not to be confused with even actual shorter glass fibers, which would be milled glass fiber. That's even smaller, even shorter. And so just to point out, the rest of this presentation, I will reference short glass fiber. It refers to standard glass that is used in our materials. Okay. Short glass fiber. These fibers are used to boost our mechanical and thermal properties of the base resin. There are some things to consider and remember based on the last couple slides as well. Anisotropic shrink. The aspect ratio of the fibers, meaning its length is different from its diameter. It makes their cylindrical in shape. And so because of that, they tend to line up when they're flowing into your part. And when they line up, so think logs going down a river, they tend to line up. So think as they line up, when you go to, the part goes to shrink, all of the fibers that are lined up in the flow direction are going to inhibit some of that shrinkage. So you're going to get less shrink in the flow direction than you will in the cross flow direction. So that's how you end up with non-uniform or anisotropic shrink. And because of that, you're more likely to experience warp. So those of you guys that have molded parts out of glass fiber reinforced materials, you're probably aware of its likelihood or desire to want to cause warpage issues. And so we have a few ways to go about fixing that, but do note that that is a common normal thing that's going to happen because of the fibers themselves and their shape. Impact and elongation, as I mentioned, you see an increase in your stiffness and strength. You're generally going to see a decrease in your impact and elongation. The other thing to keep in mind that I've not mentioned yet is going to be the rough surface. So even if you bury the glass pretty well, you're still going to rough up the surface just a little bit. And in most cases, you actually rough it up quite a bit. So the glass fiber ending up on the surface is going to create what we call a rougher. I use subjectively less appealing. Some people like the look, the more matte, roughed up look. And in certain markets, that might be an appeal. So I use subjectively, but do know that it's going to affect the way that the part appears. And that's shown very clearly over on the right-hand side. You can see the top one is an unfilled 6-6. So you can see it's kind of nice and shiny. There are some fingerprints on it if you notice, but it is pretty shiny and easy to look at. It looks kind of polished. And then you look at the 30 glass and you can see it's very much rough. It's hard to make out the lights, which is what's on the ceiling that's actually reflecting off the part, but it's difficult to make those out because the surface is so rough. It's not polished and allowing the light to reflect off it as easily. So keep that in mind. It is going to change the appearance. Part of that too, as a side note, would be it could also affect the way a color looks. So if you had a color match done in an unfilled product and now you use a glass filled product, you're going to potentially change the way that the color is perceived because the surface is rougher now. So just keep that in mind. If you end up going to a glass filled product and you have a highly regulated color that you're using, you might need to get it color matched again, just as a point of reference. But all that to say, performance boost if you need it in stiffness and strength area using glass. So showing that, what that looks like, you can see a large increase in your strength. So this is going to be an unfilled versus a short glass filled PA66. So you look at the unfilled in the dark blue, it's showing a tensile stress or tensile strength of 81 MPa. When you jump all the way to 33 glass reinforced 6.6, it jumps to 205. So you see 150% increase. So a real good increase in your strength performance. And if that's what you need out of the part, that's what you get. And then the downside would be glass doesn't like to elongate. It doesn't really pull apart and stretch. So you can see that you see a big drop. Unfilled at 29% elongation, drops down to 3%. And it's 3% for 13 and 33. Glass doesn't move, want to move regardless of the amount that's in there. So keep that in mind. You lose your elongation when you add glass to something. Okay. And then, as we mentioned, mineral also sees an increase in your stiffness and strength and a decrease in your elongation. So now more data to show that. So same materials, but now the addition of a 40 mineral 6.6. So you can see going from 81 again at unfilled MPa, it jumps to 103. So an increase, but not as dramatic as you get when you add glass. And then 29% again for your elongation, and it drops down to 6% when you use mineral. So increase stiffness and strength, lower impact and elongation. And then your shrinkage, again, back to the short glass versus your unfilled. You can see if it's an unfilled product, shrinkage is at 2% or 20 thou inch per inch shrinkage, but you can see flow and cross flow are at 2%. So if flow and cross flow are the same or just about the same, that's uniform shrink, anisotropic shrink with it being unfilled. Then you move to the 13 glass and the 30 glass. So you can see the 0.4 and the 0.5. Those are in your flow direction. So you can see it does not want to shrink nearly as much because of the glass getting in the way. And then in your cross flow direction, you're looking at 1 versus 0.9%. And so, or 10 versus 9 thou. So a big difference. So you have double the shrinkage in the cross flow direction compared to the flow direction. So this is where you have non-uniform shrinkage, anisotropic shrink. That right there is what causes your material to want to warp when it's being made. And then we bring in same data, but include the mineral as well. So we said that the mineral does not add to anisotropic shrinkage. It tends to keep it more isotropic. So you can see with the 40 mineral, you're at 1.1 and 1%. It's because minerals tend to not be cylindrical in shape. They tend to be more spherical in shape and some variants of it, but generally more spherical in shape where you're not going to have that issue with it lining up with the flow when it's running. So you don't experience that as a problem. So if you come into an issue where you're having way too much warpage and it's not working, maybe just the boost, the little boost that the mineral gives you in your stiffness and strength is enough. And then you can maintain not having really bad warpage using a mineral. So there's a few different ways to go about doing it. Or maybe add mineral in. Or in a few slides when we talk about impact modifier, we can also help make sure that the shrinkage is not as bad. So a few different ways to go about that, but mineral will not add anisotropic shrink to your performance. Okay, so we talked about short glass fiber. We're going to talk a couple slides about long glass fiber. They're not as commonly used as short glass, certainly not, but worth noting and we're bringing up because they do play and they do have a particular niche where they fit in nicely. So for our long glass fiber, we're going to want to combat some of that loss of impact. So when we add short glass, your impact performs really poorly. And so one way that we can combat that would be to use long glass fiber. So when long glass fiber is used, it intertwines and creates a skeletal network to provide the performance boost to the material. And so because of that, when it is impacted or hit, it distributes that energy throughout the whole skeletal network of the long glass fiber versus just hitting your short glass and breaking, right? So you see a boost or a maintaining of the impact that you do not get with your short glass. Some additional information on long glass. They are made via the pultrusion process. So it's a specialized process. Not everybody has the ability to do it. That's why there's not just handfuls of these types of materials just being made readily. And so it is a special process that's needed. It creates a long pellet. So if you've never ran long glass fiber materials, the pellets are going to be long compared to your standard more round pellets that you're used to running. And so the whole length of the pellet is the whole length of the fiber as well. And that's why they're longer. And so 9 to 12 millimeter, depending on the base material and depending on who's making it, is standard for the length for a long glass fiber. That's compared to about a 1-ish millimeter for your short glass fiber. So quite a big difference. And then also, again, if you've never ran it and then you buy it, you're like, why are these pellets huge? That's weird. So it happens to be that they're the length of the fiber itself. So in addition to maintaining or increasing, I should say, your stiffness and strength like short glass, you also can see an increase in creep. You maintain some of your impact performance. And then lastly, you actually see longevity to holding on to your mechanical properties as the temperature is increasing towards the TG of the base resin. So glass transition temperature, we know that when we hit that, our materials start to be able to move. It's where molecular movement is allowed at the TG for that material. So as you get close to it, if you're looking at a modulus versus temperature graph, you'll see a drop in the stiffness as it gets close to that temperature. Because of the skeletal network and everything that is with your long glass fiber, it actually maintains that stiffness and strength a little bit better and a little bit past that TG than you get with your short glass fiber. So All this to say, long pellet that allows you for an increase in stiffness and strength that you would get with short glass, but you also get a little bit better creep performance. You maintain some of your impact, and you see better retention of mechanicals past the TG, a little bit past the TG of the base resin. Okay. And then of course some data to back that up always. So if we're looking at short glass versus long glass, this is a partially aromatic nylon. So already kind of a specialty nylon. So you can see your modulus there. So this is going to be your stiffness of the material at 60%. So heavily filled with these glass fibers. You can see the modulus between the two is actually the same. So for this particular aromatic nylon, at 60% short glass and 60% long glass, your modulus is the same. It increased it and it is the same. Now, when we look at our impact values, we use Sharpie notched for this, is what's on the data sheet to compare. The Sharpie notched impact for the short glass fiber is a 15 kilojoules per meter squared compared to the long glass that's a 60. So your short glass is only 25% of it. Or to say another way, your long glass fiber has 4 times the impact that the short glass has. So huge loss of impact when you use short glass that you do not see with long glass. Okay, so that's where our glass fibers perform, so short glass and long glass. Now we'll get kind of into some of the additional additives as well. And all this to say too, some of these we're going to go through a little bit quickly. If you have a particular need or a very specialized question, one, you can ask it at the end. We encourage that. Or we can spend hours diving into all the different additives and performances of these materials and additives. If you have additional questions, please let me know. This is a basic one, right? This is a 101 class. If you want to go further than that or have additional questions, please let me know. But that to just let you know, hey, I'm going to go over some of them, but it's not going to be as in depth as we could if we were spent time on each individual one. So just keep that in mind. So additives in general, we're going to talk about fine tuning of performance of the material. So same as fine tuning the performance when you add reinforcing agents or blending or copolymerizing. But these are done as a separate, either a master batch that can be added at the molder level or might be compounded in, depends. But one thing to note is it could be used during processing. So some additives are already in there that you don't have any control over, nor would you want to. Stuff like mold release would be considered an additive. It would already be in your injection molding materials to help aid in the release off the tool. So it would already come in there. Some of them might already have antioxidants to help with thermal degradation when you process it, to make sure that you don't degrade it when you process. And then some additives are used for end use. So your product now will perform differently because of those additives versus during processing. So additives can be used in either scenario to help either way. And then some of the trade-offs are going to be you might affect the processing. So when we're talking about flame retardant additives very briefly, but one of those things, one of the trade-offs with that is you get your improvement in your flame performance, but you about half the amount of time, residence time that you can have when you process that material. So if you already are kind of flirting with the line of allowing too long of a residence time, maybe your machine is too large, whatever it may be for that product, as soon as you add an FR additive to it, you about half the time that you can use. Some other ones, and we won't talk about colorants in this particular presentation, but colorants, for instance, you might use a master batch. Those are going to be based on, I don't want to call them lower end, but lower temperature performing carrier resins. They can't be put into higher temperature materials because they can't withstand those processing temperatures. So these are all things that we want to make sure that we're aware of. And also to say, when you're doing an additive, specifically a master batch, we just want to make sure that it's conducive to be used in whatever base resin you're looking at using. And so there's plenty of different colorants and additives that are made for different products to achieve different things. So keep that in mind. Okay, so just a handful of ones. This is the section where if you have the polymer modification one pager open, these are copy and paste notes right from it. And so we go through a bunch of different additives on that one pager and we talk about what they do very briefly. So of course, if you need more information or have more questions, feel free to ask. But stuff like antimicrobial additives, those are really big as COVID was a huge issue. And so they help to deter the growth of bacteria and fungi and other products and stop it from discoloring or producing odor. You might see antimicrobials in your PVC shower curtains. So stuff that it might already be in there and you guys aren't aware of it, but those would be some of the additives that would be there. Anti-slip additives would be your coarse particles that stop stuff from slipping. So if you have a material that has quite a lubricious surface and tends to want to maybe slip a little easier, maybe something like an olefin could be added in to stop that. Anti-stats, those are going to be a big one if you're worried about the collection of dust and dirt. So maybe you're making a lens, got to be able to, it stays in a warehouse and you have a lens there. Well, you can't have it pick up a ton of dust and have static cling to it and have the dust on there because now you can't see through the lens. So there's a bunch of different reasons we might use an anti-stat additive. And then you would just use it in whatever base resin. So you'd say, hey, I need an anti-stat for a nylon. And they would have additives for that. Another big one would be chemical foaming agents. It's kind of pictured briefly a little bit on the right-hand side. Essentially what it does is it creates those air pockets in the material to help with sink mark removal or warp control or weight reduction. So if you're having issues with sinks, maybe the part happened to be designed a little too thick in a certain area and we're not able to achieve or fill out the part and not have it create a sink there, maybe a chemical foaming agent could help. So there's a few reasons you might use those. And those ones are very specialized. So if you ask for it, you'll probably get a lot of questions about it, but just one of the additives that are available to help you achieve different things in your product. Nucleating agents, some of these come inherently in some of your polypropylenes. So if you look at some of the polypropylenes that are out there, they'll come nuke and anti-stat already. It's pretty common for them to do that. But your nucleating agents will help reduce your cycle time. So it makes areas for the crystallization to start happening and happen quickly. And then it happens more uniformly because of those site locations for it to start to occur. So nucleating agents are used commonly in propylenes. You might find that some of your nylons are nucleated to help cycle it faster. And so they're used pretty commonly. So these are just a handful of some common ones you might see. Again, if you have the one pager open, it'll go through a bunch of other ones as well. Okay, so now impact modifiers. This one, I put it under additive. Maybe some people refer to it as more of a reinforcing agent. Either way, it works. But impact modifiers would be one where I'm going to spend a couple pages on as well to go over its performance. So glass, you increase your stiffness and strength. You typically lose your elongation and impact. Impact modifiers do the opposite. So they're typically made of an elastomer. They're some form of a rubber, have a TG well below room temperature. So they're very flexible, very high impact. And so when you add them to your product, you increase your impact and elongation. But then same thing, the opposite reaction would be that you lose your strength and stiffness. So if you're hitting the strength and stiffness you need perfectly, but you're not quite there on impact, adding your impact modifier is going to lower the stiffness and strength performance. So you'll need to find the balance of what you're looking to achieve with it. Or you might just want a really high impact product. And so nylons are big in being impact modified. So if you've used a nylon that's what they call toughened or super tough, some common grades out there for that, this is what they have added. Impact modifiers have been added to them to be toughened or made super tough. The nice thing about your impact modifiers is they are also more spherical in shape. So they help with your anisotropic shrink. They do not line up in the flow direction like glass and helps you achieve more uniform shrink. And so impact modifiers can be added by themselves. So if you just want a really good impact nylon or other product, it can be added that way. Or if you want to increase your stiffness and strength, but not have as bad of loss of impact and have anisotropic shrink as bad, you can add it into glass-filled products as well. And that's what I have some data on the next couple slides. You can do glass and impact modified grades and achieve different properties by adding those in at different amounts. So with data for that, so we go back to our short glass fiber, but we also include short glass fiber and impact modified values to show you this. So again, your unfilled, you can see I'm using the same grades. So the unfilled at 81. When you move to a 13 short glass fiber, you jump all the way up to 115 tensile strength. When you add an impact modification, it still improves. It's still enough to improve your stiffness and strength, and it gets up to 110. So you're still above what it was unfilled. But then you look at the big change down below is going to be your impact. So your unfilled grade is performing at a 6 kilojoules per meter squared impact. Your glass-filled grade, showing the loss of impact, right, is 5.1. And then when you look at a glass-filled and impact modified grade, so you're kind of getting a combination of the two, right? Your impact jumps all the way up to a 12. And so able to achieve higher stiffness strength, higher impact, and with the next slide, not have as poor loss of anisotropic shrink. And so if you look at unfilled again, 2%. Then we look at the glass, so 0.5 and 1, it's half. Then you look at your glass filled and impact modified, you're at 0.7 and 0.8. So the impact modifiers, those little pieces of rubber, disrupt the flow of the glass, so the glass can't line up as easily as it would like to. So they're kind of in different directions. This helps to allow for it to be more uniform shrink. So you achieve, not only do you achieve your better stiffness and strength, your better impact, you also have more isotropic shrinkage. And so impact modified glass filled grades are really useful in achieving a lot of those different things. So again, depending on what we add to it, what we're doing to it, we can change a bunch of different properties to hopefully achieve what we're looking to achieve out of it. Okay. All right, and then the next additive we're going to talk about, briefly just give some data. I did a whole presentation on outdoor plastics and testing and all of that, so a good one to go watch. But a UV additive, real quick slap with some data on this. So if we're looking at, this is an ASA versus an ASA with a UV additive. And so you can see this is a comparison of delta E. So delta E, delta being meaning change. So delta E is the change of overall color shift in a material. So when they measure color, typically they'll use the LAB scale. So that would be your lightness, that would be your yellow blue, and that would be your red green. And so what they do is they'll take what it was to begin with, then they'll take, after they age it, so that's the case of these two values on here, they'll take those values and read it after it's gone through aging. So in this particular study, they exposed it to 24 months of UV, and then it compares your lightness, your yellow blue, and your red green, and then gives an overall score in shift of color. So if you want it to shift less or be less color shift after UV exposure, you want a lower delta E value. So in this case, your ASA with no UV tested at a 2.21 delta E. Your ASA with UV additive in it tested at a 1.32. So it did not change its color as dramatically as the one without the UV additive did. So all this to say, I just added a UV stabilizer in it. We exposed it to UV. The material with the UV stabilizer was able to hold on to its color better than the grade without it. And so we have lots of cases of this. We've got lots of weatherability data on a lot of different materials when we add UV additives to them. This was just one of those situations where I wanted to provide some data to kind of show what that looks like when you add a UV additive to it. Okay. Then we have the last additive that I'm going to cover briefly. Again, if you have more specific questions, please feel free to ask or get with us afterwards. But flame retardant additives is going to be the last thing I cover briefly. So I have to start by explaining plastics in general, if we're not as familiar with them being, more hydrocarbon based. They're prone to combusting and burning. Some materials have a chemistry that allows them to have what we consider a high enough limiting oxygen index, or sometimes I think the data sheets on Prospector just say oxygen index. And so what that means is that's the minimum amount of oxygen that has to be surrounding the part or in this, however you're testing it, to allow it to continue to burn. So if you're trying to have a fire, it needs oxygen to continue to burn. So in the case of these materials that require a high level of oxygen that you're not able to achieve in your everyday, and I guess I should give a few extra data points, right? Everyday oxygen, the average that you and I are sitting in right now is about 21%, 21, 22% oxygen. So any of these ones that you see above this 30 line, they require more oxygen than what is currently found in our everyday air to continue to burn. So these materials above the 30 line are considered self-extinguishing, meaning that you don't have to add anything to them and they will automatically put themselves out because there's not enough oxygen available to it in the air to continue to burn. So your LOI value gives you an idea of how much oxygen is needed. Again, if it's above a 30, if you're looking at a data sheet for some of these specialty materials, it's above a 30, you go to light it, it's not going to continue to burn. So you don't have to add anything, which is great. So when you go to get, if you're making a part for UL, it's got to be V0, 5VA, whatever flame rating you might need. The materials above the 30 will already hit that, nothing added to it. In the case of the materials, which is the majority of them, as you can see, that are below that 30% line, they will require a flame retardant package to be able to achieve a flame rating. So you can see a lot of them here. One thing I want to point out, as you can see, the lowest value on there is going to be your POM, so it's your acetal. That's at a 14. So if you try, we can try with our greatest might. Acetal will never be a V0 5VA flame retardant material because it just burns so easily. And so all the other ones that are a little closer though to the 30% line, we can add a flame retardant package to it to achieve a flame rating that would be deemed acceptable for V0 5VA. So wanted to preface by saying not all materials require a flame package as an additive. Some do. And the ones that do could be the ones below that 30 line, with the exception of acetal that will never achieve a V0 5VA. Okay. And then the last one is, I'm not going to go into the chemistry or all the different flame packages or the, UL94 flame testing. There is a UL presentation on that we can provide if you'd like. But the reason that we use them or why we would have them is simply because if something doesn't continue to burn and then light other things in your house or your office or your car quickly on fire, it allows you a greater escape time. So they did a study back in 2009 and found that when using materials that are flame retardant or self-extinguishing materials that are inherently like that, it provides you 15 times greater escape time. So 15 times the amount of time to get out of a house if things are lighting up and are on fire. And we want that. And so that's why a lot of really big things, so like your printers, your televisions, stuff that are using your electricity that might spark, might light up, we want them to not burn so easily. And so because of that, a lot of those products will utilize materials with flame packages in them. So stuff like your housings on a printer might be an FR ABS or an FRPC or whatever it may be. But we would add a flame retardant package to it to achieve a flame rating that would be required for then the component to be UL listed. And so again, didn't go through the chemistry of it, didn't go through all the testing that is available, and it can warrant a further discussion as needed. But basically, to put out, we want it to not burn very quickly because we want to be able to get out of there if it does happen to light on fire. So, and that was the last additive. So with that, that is what I had to present to you guys. So thank you.
Thank you, Andrea, for your comprehensive presentation. At this time, if you have any questions, please type them in the questions section or raise your hand and I will unmute your microphone and you can ask your question out loud. We have Jim Werwell, Technical Development Engineer, on hand to assist Andrea with questions today. As a reminder, as you type your questions, please remember to complete the survey at the end of this webinar. Your responses will help shape future Chase Knowledge webinars, and we welcome your feedback. Also, please be sure to check out our blog page at chaseplastics.com/blogs and past webinar recordings and future webinar announcements and registration at chaseplastics.com/webinars. If you'd like to have a custom Chase Knowledge topic presented to your organization, please reach out to Andrea or myself. So let's get to the questions here, Jim, if you want to read those off and either you or Andrea can answer those.
Perfect. So let's start with Jennifer's question. Jennifer wants to know how long glass fiber compares to non-glass filled in terms of impact strength. I'll jump in and start that question a little bit. So we'll start with long glass fiber compared to short glass fiber there. You do retain better impact strength in long glass fiber than you do in a short glass fiber scenario. But as it pertains to unfilled product, that can vary a little bit. So actually, Andrea, do you have some good numbers on that?
Compared to unfilled. So that was the one thing. So thank you for that question. I realized I did not put the unfilled value. I don't actually think we have an unfilled value for that particular material. I could find some data on it. It will depend on the base resin. So if you're starting with a base resin that is very impact or has really good impact, like again, like a PC, you'd start with a PC, you'd drop down to like, which would be anywhere from depending on the grade, 12, 14, 17 foot pounds per inch impact on a PC. You add glass. We have one grade of glass filled PC that tests at a 2 ISOD. So it drops all the way down to a 2. Now I'd have to get values for your long glass, but if I had to guess, it would probably be somewhere in between the 2 and the 17. So your really highly impact resistant materials, you're going to fall somewhere in between the glass and the unfilled value. If you're starting with an already brittle material, they're all going to be about the same, maybe even a slight improvement over the unfilled base product. So unfortunately, it's not an easy answer because it does depend on what base resin we're using. But if you had a particular material in mind, we could certainly look into those values. But again, if it's super impact resistant material, you're going to see a decrease for both, though a better retention with long glass versus your brittle material, which you might just see an increase with both of them over an unfilled.
Yeah, it's really, it comes down to the material's ability to dissipate that energy across the system, right? So the short glass fiber just, it's good at taking a brunt load, but it's not good at dissipating the energy through the system. Long glass fiber can transmit that energy through the system a lot better. And then the polymer itself, as Andrea said, it's a ductile polymer to begin with. Usually that energy can be dissipated out relatively easily by the polymer. So the long glass will take some of that down, but you will preserve it significantly more than in the short glass.
And Jim, if
Really
I
good
can
question.
interrupt real quick, I'm sorry. We do have Joseph West has his hand up. So Joseph, I'm going to uh, unmute your microphone here, and you can go ahead and ask your question out loud.
Oh, okay. I was just typing what questions I had in the chat, but the in the question section. But I think the one I was probably most curious about were do the long LGFs do they get shredded during the molded process, like going through gates? And we kind of had some experience with this where we were you know, doing some sampling with them, and then we just found by the time they got in the part after going through the gates and everything in the mold that they were just shredded.
So that's a great question, and the answer is in and you've already answered this for yourself. Yes. Um, Anytime that we're processing glass fiber, we're running the risk of degrading the glass fiber length through shear. So when you're molding long glass fiber product, there's a huge benefit to be gained if you're considering your feed system, your runners, your gates, your sprue. Um, if you're considering that. So you want to make sure that there's as little restriction to the flow as possible. You want to minimize 90-degree turns. If you can, you'd like to add some generous radii to the runner bends themselves to preserve that fiber length. But yes, that's a very big concern. In my past life, I used to mold some long glass fiber. Um, we ran into some problems with that where we did some burn off testing and we had a lot of glass powder and
Oh,
not
okay.
so much retention of long glass fiber.
All
High
right.
back
Is
pressure and things like that on the injection molding machine can also chop that fiber up as you're plasticating and building your shot.
okay. Well, are there any like white sheets or guidance design guides for mold design for if you're wanting to consider some glass fibers at all, regular or long?
Yeah, we can follow up with that. I'm sure there's some documentation out there to give you some ideas, or
Okay.
the technical development engineer in your region can also sit down and have a conversation with you and look at some of those things and probably pass on some best practices.
Okay. Great. Thank you. I typed the rest of my other questions in the chat. So
All right,
thanks.
perfect.
Yeah, that's the one thing as just to add to what Jim was saying, there is some special processing best practices that you will have to follow when you do long glass, specifically because the fibers are long and they are easy to break apart if you are abusing it when you process it. And so, yeah, we would have something in place where they would, say, hey, we recommend you look at making sure you're doing this, and some of the things that Jim had kind of already mentioned. So hopefully where you're getting the long glass fiber from, they're providing those words of wisdom when it comes to processing them to you.
We'll take another one out of the chat here. What kinds of additives are normally used as a UV stabilizer in glass interlay? Does it change the haze or YID, yellowness index? This comes from Michal Shah.
For that specific product, I'm not sure. UV additives come in 3 buckets typically. You have your screeners, which are going to be commonly carbon black, or TiO2 should be for white. So that's common. If it's being used in something like she said, I think it was a PC, but it was a composite or something. So when you're looking at standard PC that's UV and clear, you would obviously not be using carbon black. They have HALs, which are used for UV stabilization. That's going to be the most common, and sometimes in conjunction with UV black. There's a few different ones that would be used essentially. Generally, if you're needing something with UV performance, we will recommend that you get something that has it compounded in. Even more if you're using clear products and you're wanting them to maintain that clarity, because that could be an issue. And with UV exposure, you're going to see an initial yellowing. First, it depends on the product, but you'll see some yellowing. That's what will be the color shift in your clear products versus your non-clear. So the ASA that I gave is a non-clear product. So the data on the delta E doesn't have to do with yellowness index necessarily. It measures the yellow change, but it's not clear. And so for the UV additive, it would help to make sure that it's not discoloring in that way. So it's not turning as yellow. It's not a great answer to the question, I recognize, but they would have different additives that would be used. Generally, we don't recommend that you add it at the press to do it. We would recommend that you get a compounded grade for it to make sure that you don't affect the clarity of a polycarbonate. Because if you're using a UV additive that's not recommended for that, you could end up with a cloudy part before it's even seen any type of UV exposure.
Good question. All right, we're going to move on to another one from Mr. West. How do FR additives affect residence time? This is going to be a similar answer. It really depends on the FR package being used in the resin package that it's being used in. You can have some FR packages, red phosphorus, for instance, that can have significant reductions in residence time and can lead to some volatile situations if not processed correctly, while others are more robust to time and temperature. A lot of scenarios are going to call for around a 5-minute residence time target or less when you're dealing with FR polymers, but that is an arguable rule of thumb.
Mm-hmm. And I would say for anything, this is more specific with color as well. It has everything to do with what's being used in the additive to achieve what you're looking to achieve. So if you're getting anything as a master batch, it's coming in a carrier resin. Hopefully, if you're using higher temperature materials or more specialized materials, you're using a carrier resin that is that same base type. But whatever's within it, or the additive itself, that is what the additive portion of it is, what is going to be that will degrade thermally typically. That's the same thing that happens with colorants too. They'll use pigments. So whatever the composition is of the additive itself, that's what's affected by your processing temperatures. And sometimes your shear, there's a few different things where it can affect it, but it's basically the chemical composition and what ingredients they're using to make those additives that are more sensitive to heat and processing than the base resin itself. And so when you add it in there, it's more likely to degrade. It's a little less stable than the base polymer. And so you see that reduction in residence time. And sometimes they ask that you see a reduction in temperature. They might have recommendations when you go to use these additives that change your processing just a little bit to make sure that we're protecting it. In some cases, certain flame retardant packages specifically can't be used in certain materials because they process too high of a temperature. So you get kind of can't process it too hot. So in some cases, certain additives have to be used for FR that you can't use in others. And then the residence time with that too. It's just basically we're trying not to degrade it. We don't want it to break down and degrade. That's why those recommendations would exist.
Another good question. Um, let's continue on then. Another one from the chat. We've got Cody Bates wanting to know. Oh, I got ahead of myself there. There's the first one. Are there any environmentally friendly green fillers? There certainly are, Cody. You can find anything from wood pulp, hemp, flax, jute, um, in a number of other recycled paper.
Mhm.
There are a number of fillers that are available on the market, reinforcement packages on the market that are natural or recycled in nature that lend themselves to being more environmentally friendly. And even fiberglass itself, for example, in Valier, one of our manufacturers that we represent, they recycle their own scrap from their fiberglass production line, and then are able to feed that back in as recycled content into their resins. So aside from the natural fibers, there are other ways in which we can be more environmentally friendly with our standard reinforcement packages. What you'll find is you typically don't get as strong of a reinforcement or as big of a jump in your mechanical properties from the thing or from those fibers like flax and jute and hemp. They can be a little trickier getting consistent sizing and having continuity of supply at very large scale. Um, but they are out there. They are used. Um, cosmetically, they bring a different look to the table, which in years past hasn't been as attractive. But as there's more um, press and more um, what's the word I'm looking for? More recognition of the need and want of those products. They are able to differentiate themselves by their look. Where it used to be something that we would consider maybe less attractive, is now being looked at in a different light because it becomes more obvious that it's a green or a natural reinforcement. So that trend or that paradigm is shifting.
The only thing I would add to that would be if you are looking for that particular type of product, they're generally called biocomposites. So if you're looking on, brochures or information on green products, they're normally grouped. I guess it also depends. Sustainability is a whole another animal. But depending on how the supplier markets it, generally biocomposite is the term that you'd be looking for if you were looking for something that is agave, coconut, flax, hemp filled and reinforced within a material. So we've got plenty of them that are propylene based or polyester based that are then filled with those. So biocomposite is generally the term that they'll get grouped under. So if you're looking for something specifically, you could use that term.
Awesome. Thank you, Andrea, for adding on to that. Um, looks like Naveed had a very similar question to what was already asked concerning the long glass fiber and what happens to that. Does it get degraded? Um, and so I think we're going to move on to that or from that. The only maybe a
Mm-hmm.
little difference to this question is, do they get broken down for that 9 to 12 millimeter length? It does
Mm-hmm.
start as a continuous glass fiber and it gets pulled through a resin stream through a pultrusion process. And so it is cut then to that 9 to 12 millimeter length. And what you'll find is that the fiber length of the glass is equivalent to the pellet length in those scenarios. And then from there, the processing can degrade that fiber length from there. Um, so good little addition to that question. Next one from Dylan Siriani. How does color additive affect material properties? This is also kind of a nuanced answer because it's not only the colorant, but then the carrier resin, if it's being added as a master batch, that can have an effect. Um, Depending also on the type of colorant, because different pigments are going to have different aspect ratios. So pigments that are low aspected and small particulate size don't have as much effect on the mechanical properties as fillers that have an aspect ratio or are large platelet or something along those lines. Some are small enough they can act as a nucleating agent. Some are large enough that they can act as a contaminant. Um, and then the carrier resin as well. If the carrier resin isn't as compatible with the system, that can also act as a contaminant. Um, you can also impart some other properties to the material through that colorant package. As Andrea was mentioning, titanium dioxide, carbon black. So not only will those affect your color, but they'll also impart UV stability. Other effects, titanium dioxide is known to degrade glass fiber length. So in scenarios where you need TiO2 as a brightener in your colorant system to achieve the color you're trying to hit, and you're using a glass filled system, you're actually maybe decaying the mechanical properties due to the attack of the glass fiber from the abrasiveness of the TiO2, the titanium dioxide. So it depends really on the colorant system and the resin, um, and then the base resin.
And you should be, not to make it sound so scary, right? You're using generally, or should be, I should say, using it at such a small concentration that it will have these effects on it, but it shouldn't act as though you're using an entirely different material now. And so pigments, as Jim mentioned, if they're more abrasive, tend to attack the glass a little bit. So you might see the lowering of properties because the glass is now getting broken up a little bit. But we're not talking you're going to lose half your performance. We're talking about color that you're adding at maybe 2%. And so it's not something we're like, oh, I got to expect to lose half my performance. Most of the time, the changes are so small that they would be captured within a standard lot to lot variation of these. There are some cases where you might see it outside that, but generally speaking, within the expected variance of lot to lot performance of your material.
Yeah.
So yes, all effect, very good effects, but not to scare you into not using color because it's, going to be such a dramatic effect that you would not, the material isn't going to perform anymore. So we don't want it to sound like that.
Great point, Andrea. It's used every day, all over the place to great effect. There are just some nuances to be aware of.
Mhm.
Cody had another question concerning post-consumer fillers. Now, I think we already touched on that a little bit, especially as it pertains to things like the recycled scrap from the fiberglass production process. Same thing. Carbon fiber can also be reclaimed and reused as a filler, although you start to lose some of the homogeneity, um, i.e., you might get some dispersion in terms of filler size, fiber length, things like this, fiber diameter. Those are tried, obviously those are tried, attempted to be kept as consistent as possible, but you might see a little bit wider spread as you get into the post-consumer products like that. In terms of the glass, that goes back through the furnace, and that comes out as the exact same size and shape of standard glass fiber. So in that case, you don't see really a significant change at all. But those do exist, and there is mass balance approaches in which you can get credit for those green initiatives there with those post-consumer fillers. Let's see. I keep getting scrolled up in the.
They've got a bunch of good questions.
That's true. Nathan Bartlett wants to know about how fibers and fillers affect viscosity
Mm,
at
okay.
processing temps.
Yes.
That's a great question. You're now trying to flow something that doesn't itself flow through an orifice. So it is going to increase your resistance to flow. You will see higher pressures on your molding machine. Um, that's a pretty common scenario to run into.
Mhm. It's why you also see they limit the max amount. So on the slide where there was 60% glass, short glass and long glass, that's about as high as they're going to attempt to go because glass, as you mentioned, doesn't flow. So if you're trying to flow a polymer into your machine and make a part, which is kind of the whole premise of processing the material, if you have it full of stuff that doesn't flow, think of it as the logs, like the analogy I used, a bunch of logs. If your river is full of 90% logs, they're going to start getting jammed up and they're not going anywhere. And so you can't do that. You need to you need to have enough polymer to allow it to flow, but it does increase your viscosity, resistance to flow, and then you'll see that in increased pressures and stuff to try to get it to flow like you would something else. The fillers are not as bad, but you're still adding stuff that doesn't flow. And so you'll see a similar effect.
And so that's a really good caveat into Joseph's question, wanting to know about mineral fillers affecting then the color and finish like glass filler or glass fiber does.
Mm-hmm.
Um, and yes, that can certainly be an effect. Um, Depending on the mineral, it can act as a brightener or it can act as um, a color shifter. Some mineral has a yellow, whitish with a yellow tint. Some mineral more gray. Some things like your carbon is very black. So at high loadings as well, you can start to see that at surface a bit. You can see some matting out of surface. And certain minerals will also change the tactile feel of the surface of the part. For example, a part highly loaded with calcium carbonate will have you can notice a change in the surface feel. It will become silkier in a way. So it can certainly affect that surface and affect the color.
Mm-hmm.
So that's again an important part why we would want to color match with the intended resin package. Another question from Joseph West, um, wanting to know, because some resins are prone to yellowing, do UV stabilizers help that, even for indoor products? Um, yes, they can. A lot of what you might see indoor that's yellowing, that's still a UV um, color change pathway or degradation pathway. This is really noticeable in things like ABS in its natural state. It has a tendency to yellow pretty hard under UV. Polycarbonate can do the same thing. So the UV protection packages that are employed in those, and again, if I would urge you to look at ASA instead of ABS for UV applications. Um, but in those scenarios, you are buying time before you start yellowing at a higher degree with those additive packages.
And they call it, if you've heard the term filtered light. And so it's the same phenomenon that will happen inside a car. So light still gets inside a car. If you've been driving around, even if the windows are up, you can still get a good sunburn if the sun's shining real nicely. So it's doing the same thing to the plastic. And so they call it filtered light, but it's still UV and it's still attacking the stuff that's inside your car and inside your house. So those of us that have a house that's old enough to have a thermostat on it, a housing on the wall. If it's old enough, it was either probably made out of a PPE or an ABS. It's probably pretty yellow by now. And so, yes, adding the UV additive though would allow us, it would take longer for it to degrade to that level. But certain materials are still going to yellow. So we would encourage that you stay away from them.
I'm going to circle back real quick. Dylan had a quick question about what do I mean by aspect ratio. Length to diameter, essentially. So what does the actual particulate or particle look like? Is it a rod? Is it a sphere? Is it a platelet? That aspect ratio is essentially its length to diameter ratio. So, for example, talc is more like a grain of rice, and it imparts some physical reinforcement to polypropylene, whereas like a calcium carbonate being more of a spheroid. Yeah,
Seeing if I had those pictures aren't the best to show that. A very dramatic version of it is going to be the aspect ratio on those long glass fibers.
yeah. So that there you go. So very long, small diameter. That's a high aspect ratio. And so because that will span then across multiple polymer chains, you get reinforcement across the chains. Things that have smaller aspect ratios don't cross as many chains and then don't impart the same um, physical property bump. So colorant is way less pronounced, significant orders of magnitude less pronounced than fiber. So that's what we're talking about in terms of aspect ratio.
It's basically to say if it has a high aspect ratio, like this long glass fiber would have, means it's really long, has a really small diameter, and so it's be very cylindrical in shape. Your ones with really low aspect ratios are more round, more spherical in shape versus cylindrical. That's essentially what it is too. On a more
Yep.
basic geometry level, I suppose. Yes.
And now when it comes to that will also affect your shrinkage. So fillers with higher aspect ratios will have a tendency to have more anisotropic shrink, whereas fillers that have a lower aspect ratio will typically exhibit more isotropic shrink. So that's going to roll us into Cody's other question about glass beads.
Mm-hmm.
Glass bead is a lot of time used as a shrink and warp modification. Because it's very low aspect ratio being a bead or a spheroid, um, it will prevent the polymer from shrinking in the cross flow as much as it does in the flow direction. So it starts to then bring the delta between flow and cross flow down. And that's essentially what warp is, right? Is anisotropic shrinkage. If everything shrunk at the exact same rate, you would just have a smaller part, but the part wouldn't warp. So when we start getting that anisotropic shrinkage is when we start seeing parts warp significantly. So things like glass beads, microspheres, milled glass that has a much smaller aspect ratio, and some mineral really help to control that. And you can get a little bump in strength too with some glass bead, but not nearly as much as fiber. Leo Castellano has got a really good question. This one's a bit of a thinker. Again, we got a lot of inquiry on long glass fiber. So this is another long glass material question, wanting to know the changes in the properties if that long glass fiber material is processed on a high pressure injection molding machine versus a structural foam molding machine. Is there a noticeable change or is there shear concerns? That's a really good question. So your high pressure machine doesn't necessarily mean choked down through your flow path. It can also mean a lot of nitrogen accumulators and things like that that allow for fast movement and high pressures. Now, a lot of times that's thin wall scenarios or, tighter walls, smaller gaps, things like that. So a lot of times you may be using them in conjunction. Um, there's going to be some preference for lower shear scenarios. So the structural foam machine is going to be designed for a lower shear scenario. It's going to help you preserve that glass fiber length. You can process long glass fiber materials on standard conventional molding machines and equipment. It's just really when it comes down to setting up the process, choosing nozzle tips, lower compression screws, less back pressure, lower RPMs, driving a little bit more thermal energy through the barrel heaters than through shear, and then the tool itself, the runner system, the gate design, those play, I think, a more significant role. Now, if your structural foam machine has a low compression screw and your high pressure machine has a high compression screw, then it's more the screw driving that than the fact that it's the machine that can do those things. So I would focus more on the screw design in those interior pieces that are going to touch the melt more so than the horsepower that's driving the screw itself. Now that being said, highly long glass filled material, long flow lengths, tight walls, you might not have enough pressure on a structural foam machine to pack that. Whereas then your high pressure injection machine may be a better scenario to ensure fully densified parts. All right, I think I got that one pretty well beat with the stick.
All right. A lot of questions today. Um, Thank you, Jim and Andrea, both of you guys for all of your great answers and thorough explanations of all the questions we had today. If for some reason we didn't get to your question, feel free. Andrea's information's on your screen. You can feel free to email those to her, and she can get back with you on that. But we would like to thank all of you for taking time out of your busy schedules today to attend this Chase the Knowledge webinar. We do hope it was informative and a great return on the investment of your time. If you have any technical questions that did not get answered today, like I said, feel free to reach out to Andrea directly, and her information is posted on your screen. Thank you all for attending, and we hope to see you at our next Chase the Knowledge webinar in July. Thank you. Have a great day.